In this video, we're going to finish the notes on section 2.3 and look at instantaneous rates of change in a particular context. So in this box here, we have that the instantaneous rate of change of a function, f of x, at a value a is its derivative, f prime of x. So we've seen that before, but now let's look at the context when our function is a position function. So rather than f's and x, let's use s and t. It's convention for representing a position function, so position of an object at time t, using s's and t's. So if s of t is a position of an object, then the velocity, in other words, kind of the speed, the directional speed that the object is going, is its change of position over change of time, that velocity. So the velocity of the object actually is that derivative s prime of t. And if we want to know how fast the velocity is changing, that's the object's acceleration. So the acceleration, often denoted a of t, is the derivative or the change of velocity. Just like velocity is change of position, we want to know change of velocity, then we'd compute the derivative of the velocity with respect to t. And now using the position function, that would just be the second derivative of the position or the derivative of the derivative. And we'll be seeing this more, but this just gives us a context of where we might see this instantaneous rate of change. So let's look at this last problem here. So number 5, there's a little bit of a typo here. This should be the following graph. So number 5 says the following graph shows the height of a hot air balloon over time, h of t. Use this graph of h of t to sketch a graph of the balloon's velocity. So to get a handle on this, let's first just think about what is going on with this balloon, right? So our balloon starts at a certain height here. Then it goes down, decreases in the air. Then it hits a certain place in the air and it comes back up and goes back down. So if we wanted to think about the velocity of this balloon, it makes sense to look at the balloon at a few instances in particular. And that is where the balloon goes from decreasing to increasing. Why? Well, the velocity would then be losing height to gaining height. So by first finding where the balloon changes direction, will tell us where the velocity changes sign. So first consider where does the balloon change direction? So we see the balloon is decreasing, then increasing. So when it changes this direction from decreasing to increasing, that will be a place where our tangent line is horizontal. When we have a horizontal tangent line, what does that mean for our derivative? That will mean our derivative is 0. So where else on our graph do we have a 0 tangent line? Up here at this peak. So let's keep track of a few things. So I'm going to keep track of h of t, my height function, and my derivative, v of t. So when I have this first interval here, let's call this t1, let's call this t2, because we don't have labels on our graph. But before t2 or t1, this first interval, our height is decreasing, which means our velocity, we can look at our tangent lines. Our tangent lines all have a negative slope. So our velocity is negative. One thing you'll also notice about the balloon itself on this interval, the balloon is decreasing in height. So when the balloon is decreasing, our derivative is negative. So here as well, before T1 and after T2. So we can represent this with the following notation. So I'll just write, let's have this first input be T0. So I have the point T0, T1, T2, and T3. So I've just broken up my horizontal or my input values into intervals. So on the interval from T0 to T1 and T2 to T3, my velocity is negative and my function is decreasing. So this helps us to start painting a picture of what our velocity looks like. So now what about the interval between T1 and T2? What's happening with our h function? Well, our height is getting larger. So our height is increasing. So on the interval, I'll use another color here, interval T1 to T2, our height function is increasing. So then what do we know about our derivative at that point? What do we know about our slopes of tangent lines on that interval? Well, the slopes would be all positive. And so then if we dive further, what actually happens at T1 and T2? Well, our tangent line is horizontal, so our derivative is 0. So if we want to draw a quick sketch of what this graph would look like here, and by the graph, I mean the derivative, I'm going to label my points, my T0s, T1, T2, and T3. And we know at T1, our derivative is 0. At T2, our derivative is 0. On the interval, as we already noticed, from T1 to T2, our derivative is positive. So it looks something like, I don't know, like that. Somewhere in the positive side of our vertical axis. And then on these intervals where our height function is decreasing, our derivative would be negative. So somewhere down here. So it is tempting to want to have when your derivative is, say, negative or positive, to not have it have a peak itself. But we're going to make more sense of what it means for the derivative to have a peak in future videos. But at this point, we just want to focus on the graph of our derivative as positive, negative, or 0, which we've outlined here, based on what our graph of our function is doing. So just kind of to summarize here, we want to know, where does the graph of the balloon change direction? In other words, where is the tangent, or v of t, equal to 0? And then what we also want to look out for is, where is the graph, or h of t, increasing? That will tell us where a derivative is positive. And thirdly, what we can look for is, where is the graph decreasing rather, because that will tell us where our derivative is negative. So in final, our derivative h prime of t, this is a rough sketch, not using scales on our vertical axis, but roughly it looks something like the following. All right, thanks for watching, everyone. Please go over the notes for this entire section. Again, any parts that you'd like to review and sit longer on. And as always, please let me know if you have any questions. Keep up the hard work.